So we're talking about the strength of bases. So strength of bases and how to identify that from the pKa. Okay. And for that, we're going to compare a few of them. So let's have a look at NH3. Let's have a look at NH2R, R being an alkyl group, NH, R2, and then a tertiary amine, so NR3. Okay, so all of those would react with water in the same way. Okay, actually, let's do it like this because they all react in the same way, right? So they all form. But before I do the arrows, actually, no, let's do it like this. Let's say that for now, the reversible arrow doesn't matter. Doesn't represent the position of the equilibrium, but they all form OH minus and then the conjugate acid. And the conjugate acid would be NH4 plus, NH3 plus, and that R group stays. And then we would have NH2 plus R, and then NH plus and R. Oh, that's not true. And the R3 stays. Okay. Now, to understand how the strength of these bases is different, we needed to think, we could look at the strength of the base or the strength of the conjugate acid. Okay. And let's look at both ways. So if we look at the base, we have, let's compare just the two of them. Let's compare the secondary amine and the tertiary one, which is this one with now 3 alkyl groups. So these alkyl groups, they have a positive inductive effect, which means that they donate electron density to the lone pair.
Okay.
So this causes the lone pair to be even more negative for the tertiary. As a consequence, it's more reactive because we know that it's this lone pair that attacks the DH plus. So this will tell us that the tertiary is the most reactive.
It's the stronger base.
Is the strongest base, exactly, because in terms of reactivity, it would be the strongest base. Okay, because this positive inductive effect we can say has, so this what is called plus I, it has a destabilizing effect on the lone pair.
Yeah.
But it's not a bad thing, destabilizing, it just makes it more reactive.
Okay.
So we know that, well, this reaction, the last one of the tertiary, it would react a lot more in this direction compared to the secondary, compared to the primary, compared to the one that doesn't have any stabilization or destabilization group. So that's one way to think about it. But the other way, which is actually what then we need to know for the pKa, it's to look at the
conjugate acid.
Move my camera. Yes, it's to look at the conjugate acid. And we can look at it in the same way. We just really need to think about that R group. So that positive inductive effect, what effect does it have? So let me move the screen a little bit here to have a bit more space to write down. And all of these are really like logic processes that then we can use to work these relationships out, because otherwise it's just remembering, I think it's just really difficult. But let's compare again the conjugate acid, let me get in another color, of the secondary and the tertiary amine. So we have 2 hydrogens and the 2 R groups with the positive charge. And then for the tertiary, the conjugate acid of the tertiary would be N plus with just R groups. No, it's 1 hydrogen and 1 R group. what we need to think about is, okay, this R group, it's alkyl, so donates electron density. But what effect does it have on the plus?
It's
So
making it more neutral.
more neutral, exactly, because this plus inductive effect, it makes the intermediate more neutral. And we know that if the intermediate is more neutral, it's more stable. So if it's more stable, it's more likely to form.
A weak
And if
acid?
it's more stable, exactly, it's a weaker acid.
Okay.
It's going to be a weaker acid because it's more stable. It doesn't want to get rid of this hydrogen. It's stable as it is. Because, yeah, so more stable also means less reactive.
Okay.
Okay, which means that it's more likely to exist. So if we think it in this way, we either think the position of the equilibrium, or we think, okay, wait, if it's more stable, it's less likely to give off its hydrogen, so it's going to be a weaker acid. So this is going to have the largest pKa. Or overall, we can just summarize it as, to remember the strength. So the stronger the base, the lower, no, the higher. So the stronger the base, the higher the pKa, because the stronger the base, the weaker the conjugate acid. Remembering like this, I think it's difficult because we really need to work out and understand either why this base is strongest, and that would be the effect of the groups that substitute that base, or understand why these groups would affect the strength of the acid. Okay. So let's do an example of what we just explained. Let's apply it and just try to understand the strength of acid. So here we have two examples. We already briefly mentioned the first one, but let's look at it again. So we're talking about guanidine and thinking about, okay, wait, how do I know where would the equilibrium lie, if it's on the right or on the left-hand side? Well, we need to think about destabilization. So, well, of course, it would react as a base because the lone pair of electron of the nitrogen will react with that H+, and as you can see, would form the protonated one. But let's have a look at what happens to this positive charge. So as we have from the diagram, we have a resonance structure. So the positive charge, it's basically delocalized onto all the nitrogens. Look how it's present onto all the nitrogens. Which means that if it's delocalized, so this is a positive mesomeric effect, it means that it's stabilized, because the positive charge is not on one location only, but it's spread between 3 bonds, so it's kind of less concentrated, therefore more stable. But if it's more stable, it means that it's less reactive. So an acid, a conjugate acid that is less reactive, means that it's going to be a weaker conjugate acid. And that's why it has a quite high value of the pKa. So this suggests the equilibrium will lie on the right-hand side, because the conjugate base, it's pretty reactive. We could think it in the opposite way as well, like, okay, why is it so reactive, the base? Not only because of how stable the product is, but because each nitrogen has a lone pair of electrons, right? So they can donate those electrons to this nitrogen to make it a little bit more negative. So this lone pair is even more negative, and this makes it more reactive. But in this case, understanding, I think, the stabilization of the conjugate acid is a bit easier. Positive charge spread along all of the bonds, delocalized, therefore more stable, therefore weaker conjugate acid. And this tells us that that's going to be more present, equilibrium on the right-hand side, which means that the base has just reacted more. So that suggests that it's a stronger base. Okay. The example below, it would be actually the opposite, but let's look carefully step by step. So first we have a resonance structure of this amide, because the lone pair of electron on the nitrogen can delocalize in different positions, so it can go onto the oxygen. Okay, and of course, if it goes on to the oxygen, it has a formal negative charge, and this formal negative charge will make it more reactive towards the hydrogen. That's why it forms this OH, as we have there. It's the oxygen that has picked it up. Okay, but let's think about the effect that this positive charge, like where does this positive charge go? Okay, so the positive charge now, it's there is no really delocalization that is taking place, okay, because despite being a positive charge on both, yeah, it's, let's say, always present, that positive charge. It's on the oxygen or on the nitrogen, yeah, and this will make it a lot easier to give away, let's say, because, okay, maybe that's a bit confusing because it's not a good comparison, but that positive charge, it makes this hydrogen a bit easier to be lost, okay, because if we lose that hydrogen, then the oxygen comes back to its neutral, so it will be more stable. But in this case, I think it's better to look at the base, because if we have this double bond, yeah, the double bond makes it takes away electron density from the nitrogen, right? Because it takes it onto itself. We can see it from the curly arrows. So if there is less electron density on the double bond of the nitrogen is not going to be very reactive towards the hydrogen. In fact, here is another reaction taking place. It's the oxygen that is reacting, not the nitrogen. This means that the nitrogen, it will be a very weak base, because we have this positive mesomeric effect that takes away, yeah, it takes away electron density. So this one would be less negative. If it's less negative, it's simply going to be less reactive towards the hydrogen. So this would make it a weak base. So sometimes it's easier to think about the stabilization of the conjugate acid, but sometimes it's easier to think about the stabilization or destabilization of the base, thinking about what happens to the lone pair of electron, which is what will have to react with H+. Yeah, inductive effect makes it more negative, therefore stronger base. Mesomeric effect, so I mean taking away electron density, so any electron withdrawing group, like in this case the carbonyl, will take electron density away from the lone pair, which means that it makes it less reactive towards the hydrogen, therefore a weaker base.